CHEM 1401, Practice Midterm 1, Part 2. So beginning with question number 8, it says here, the label of a bag of lawn fertilizer indicates the fertilizer contains 18% of tetraphosphorus decoxide. So first let's get that. So tetraphosphorus decoxide, that's a covalent compound with this formula, P4O10. So it's 18% tetraphosphorus decoxide by mass. If the bag's contents have a total mass of 12.25 kilograms, what is the mass of phosphorus in the bag of fertilizer? Well, the first thing, this bag weighs, it says the bag's contents. So that means it's not just tetraphosphorus decoxide in the bag, it's tetraphosphorus decoxide plus other nutrients or whatever is in the bag. And we know that it has a total mass of 12.25 kilograms, but what's out of that 12.25 kilograms, it's only 18% of tetraphosphorus decoxide. So if I do a little bit of mental math here, and I take 18%, so since it's out of 100, right, percent, so if I divide 18.00 by 100, I get 0.1800, and that's going to be the fraction of the mass, which is going to be tetraphosphorus decoxide. So if I multiply that by 12.25 kilograms, what I end up with is I get 2.205 kilograms, and that's how much actual tetraphosphorus decoxide is in this bag. So that's the mass of tetraphosphorus decoxide. So from there, it's just a matter of determining, it says, what's the mass percent of phosphorus? So I'm just interested in, what's the mass of phosphorus out of that 2.205 kilograms? And the way I'm going to determine that is by what's the mass percent of phosphorus in tetraphosphorus decoxide. So the way I'm going to set that up is I'm going to say, well, the total mass of phosphorus in my P4O10 it's going to be 4 atoms of phosphorus multiplied by the molar mass of phosphorus, which is around 31 grams per mole. I'm just doing this kind of quickly here. Okay, so that's in my numerator, and if I divide that by the total molecular mass of tetraphosphorus decoxide, I get 4 times the 31, that's for my phosphorus, plus I have 10 oxygen atoms. I'm just going to put in 16 grams per mole here, so I'm just going to use 2 sig figs to make it easy. And then that, if I was to stop there, that would give me the mass percent of phosphorus in my P4O10. But what I'm going to do is I'm going to multiply that whole thing by the mass of tetraphosphorus decoxide, so my 2.205 kilograms. And that's going to give me the amount of phosphorus, just phosphorus, that's in the tetraphosphorus decoxide, in the 2.205 kilograms. So when I multiply that out, I end up getting 0.9627 kilograms. And you can see that all the masses here are in grams. So if I take my 0.9627 kilograms, and I know that in 1 kilogram I have 1,000 grams. So my units cancel out, and I end up with 962.7 grams. So that's closest to this one here, so I'm pretty close. But again, I just rounded off for the atomic masses of phosphorus and oxygen. So there we go. So let's move on to question number 9. So question number 9, let's see here. So it says, determine the number of grams of oxygen in 338 grams of barium sulfate. So I've already gone ahead and done the math, or most of the math on this one ahead of time. So the first thing I did was calculate what's the formula mass of barium sulfate, an ionic compound, and I know that it's 233.39 grams per mole. So I went ahead and did that already, so I added up the atomic mass of 1 barium, 1 sulfur, and 4 oxygens, and I ended up with this formula mass. So in order to figure out the number of moles of barium sulfate, I'm going to say, okay, well, I've got 338 grams of barium sulfate. That's where I'm starting, right? That's all they've given me. And I know from the formula mass of barium sulfate that I can determine the number of moles of barium sulfate. So 233.39 grams of barium sulfate and a mole of barium sulfate. And you might be thinking, okay, well, that's great. That tells me the number of moles of barium sulfate, but I want to know the number of grams of oxygen. Well, I see that the ratio between the number of moles of barium sulfate and the number of moles of oxygen, I can just get that by looking at the formula here. And I know that in 1 mole of BaSO4, so my barium sulfate, how many oxygen atoms do I have? I have 4 of them. So SO4, so the subscript 4 means that I have 4 oxygen. So I'll put 4 moles of oxygen. So if I was to stop right here, you can see that grams of barium sulfate cancel out, moles of barium sulfate cancel out, and I would, if I was to stop here, I would just end up with the moles of oxygen. But I want to figure out the number of grams of oxygen. But luckily, I have a periodic table, and I know that in 1 mole of oxygen, I have about 16.00 grams of oxygen. So when I punch all that spinach, so to speak, in my calculator, I ended up with 92.7 grams of oxygen, which is this answer here. Okay, let's take a look at question number 10. So question number 10 is kind of an interesting question. It says a 35.80 gram sample of rhodium, so rhodium, here's the elemental symbol for rhodium, was reacted with carbon monoxide. So carbon monoxide is a covalent compound. It has a formula of CO, carbon monoxide, the silent killer, right? So a 35.80 gram sample of rhodium was reacted with carbon monoxide to form 74.78 grams of a compound with this general formula. So rhodium subscript X and carbon monoxide subscript Y. What's the empirical formula of the product? So in order to determine the empirical formula, I need to figure out the ratio of X to Y. You know, is it 1 to 1? Is it 1 to 2? Is it 1 to 3? Is it 2 to 1? Is it 3 to 1? You know, I need to figure that out. And the way I'm going to do that is by figuring out the ratio of the number of moles. So I can already see that I have the mass of rhodium. So if I go into the periodic table and I look up rhodium, I can find the atomic mass of rhodium. So I have 35.80 grams of rhodium. And the atomic mass of rhodium is 102 point, I just wrote down a bunch of sig figs here, so 9055 grams of rhodium in 1 mole of rhodium. So there you go. So now I've already figured out the number of moles of rhodium in my compound. So I figured out that it was 0.3741 moles of rhodium. So let me just switch my pens here. There we go. So now I need to figure out the number of moles of carbon monoxide. But from my problem, it tells me that the rhodium is reacting with carbon monoxide, and overall I get this much product, 74.78 grams. So that means that out of that 74.78 grams, 35.80 grams of it was rhodium. So what's left over? It must be carbon monoxide. So if I do that same exercise, if I say, okay, well, my 74.78 grams total, subtract 35.80 grams, okay, that's going to equal the number of grams of carbon monoxide. So I'm going to do this kind of all in one foul swoop here, so to speak. And I already went ahead and I calculated the molar mass of carbon monoxide. So in 1 mole of CO, I just add up the mass of a carbon atom and an oxygen atom, and I got 28.01 grams of carbon monoxide. So there you go. You can see that the grams of carbon monoxide are going to cancel out, and I end up with the number of moles of carbon monoxide in my sample, which is 1.392 moles of carbon monoxide. Now, I find the fastest way to get to the next step to figure out what the actual empirical formula is just divide both of these numbers, the number of moles, by the smallest number of moles. So if I divide this number by 0.3741, I end up with 1, of course. And if I do the same thing here, 3741, I end up with a number that's pretty close, very close to 4. So I can see that if the ratio of rhodium, for every 1 mole of rhodium, I have 4 moles of carbon monoxide, my formula, my empirical formula, would be RH, and then I put my brackets, carbon monoxide, put that in there, and then 4, like that. There we go. So that's my empirical formula. And again, the only way to determine that is by looking at the ratio of the number of moles of rhodium to the number of moles of carbon monoxide. You can't just use grams. Have to use the number of moles to solve that problem.